Welcome to this plenary session. It's my pleasure to introduce today's invited speaker, Eli Ben Sasson. Eli is a pioneer in what I sometimes call the modern area of zero-knowledge proofs. He's a co-inventor of several proof systems that have fundamentally shaped the field over the past 2 decades. He received his PhD in 2001 from the Hebrew University of Jerusalem, and he has held positions at Princeton, Harvard, MIT, and the Technion. Eli has been a key figure also in bringing zero-knowledge proofs to practical deployment. He was a driving force behind the development of zcash, and he's a co-founder and CEO of zkSTARKs, a company at the forefront of applying zkSTARKs to blockchain scalability. Therefore, I'm very happy that Eli has agreed to come here and talk on the rise of zkSTARKs as blockchain scaling technology. So please join me in welcoming Eli Ben Sasson.
Thank you. Thank you. Thank you, Serge. And first of all, I want to say that it's a great pleasure and honor to be speaking in front of a crowd of leading cryptographers. Everything that we're doing is based on all the collective work that you guys are pushing forward, and which once upon a time I could say I contributed to, but now I'm more like just using stuff there. So today I'm CEO of zkSTARKs. It's a company of about 200 people, slightly more, and we develop products based on zkSTARKs in the world of blockchain. And I thought, what could I tell you that might interest you and why? So what I hope you'll get from this talk is, first of all, why is it that cryptographic proofs, what everyone calls zk, I'll tell you already, everyone in the blockchain world talks about zk, and most often when they talk about zk, they actually mean not zero knowledge, but we'll get to that. So I will try to use cryptographic proofs as this generic term for all the stuff that you guys are all doing. So why is it that there's such a love connection between crypto, blockchains, and this fascinating field? I hope I'll share with you some insights or reflections on all kinds of research problems related to Starks. And I hope that you'll find the story that I'll tell you, which is my own story, basically theory to practice, just interesting. And maybe some of you who are, I'm guessing most of you are very research and academic, but probably some of you are contemplating, should I be doing this? Maybe you've started dabbling in this sort of entrepreneurship and so on, so maybe you'll get some insight from there. Okay, so I think I can summarize it, my story a little bit like the beginning of some joke. Theoretical computer scientist walks into a blockchain conference. So I did my PhD on the field of propositional proof complexity under Avi Vigdalson at the Hebrew University. I came from a family of academics, and I was very content doing academic work. I never thought that I would do anything else. And when I got to my postdoc, which I did with both Salil Vadan and Madhu Sudan at Harvard and MIT, I basically wanted to do a little bit something that they're doing, right, to change fields. And the kind of questions I ended up researching were related to the length of PCPs. But I want to stress, for a very long time throughout this story, the question of entrepreneurship or blockchain just didn't come up. So and I want to emphasize this, what kind of a sort of a gnarly and wounding path this has been and how unpredictable and unforeseen, at least in my eyes. So there was no such contemplation in saying I want to, whatever, form a company someday. The reason I wanted to investigate those questions back then was twofold. One, I just wanted to learn what these very smart people are doing and learn something new. And also, of course, the PCP really fascinated me, and I wanted to understand how it works, gain my own understanding, and there's no better way than to try and solve some problems. So I took any problem I was given. Madhu back then was very interested in the length of the proofs, so that's what I worked on. We had a number of works there with Madhu, with Salil, with Goldreich, and a few others, Prahlad Harsha, that were all around this very theoretical measure of the length of PCPs. And, it was, they were published and received in conferences like Stock and Fox, but they were the less interesting branch of PCP research. And the reason they were is because within PCP research, a lot of it back in the day, I think it still might be the case, was around applications to inapproximability. And if you think about inapproximability, it's really important that the type of constraints that are checked and the soundness at the very low level, that's where the focus is. But things like the length of the PCP was not that interesting. So these were like sort of left field kind of research results that were yet another set of publications. And that was the starting point. So around 2004, the starting point for me, like in terms of, let's say, theory to practice, was that I heard from Madhu Sudan that a student of his implemented one part of the PCP paper that we had about polylogarithmic proofs. Okay. Quasi-linear proofs with polylog application, query complexity. That student at MIT was Arnab Bhattacharya. And it sounded very strange to me. But a few months later, this was around 2006 or 7, students in a course I taught at Technion came and said, we want a summer project. So I said, well, why don't you take, so I know that one half of that paper was implemented. You want to implement something, why don't you implement this? So they implemented it over the summer, 3 students. It won the best project prize at Technion. They were happy, I was happy. Okay. The next thing was that I received this huge grant from the European Research Council. It was 1.7 million euro for me as a theoretician. And I didn't quite know what to do with it. But I already had these students having implemented something. And even I think in the grant application, it was about, I needed to justify why would I need this huge amount. So I said, I'm going to implement stuff. Okay. And at roughly the same time, Technion was interviewing this young, promising postdoc, Eran Tromer, and we wanted to bring him over. So my dean at the time, Eli Biam, said, why don't you meet him and try to convince him to come to us, work with you. So I met him at a restaurant, and I said, look, come, I have this amazing amount of funding. We can implement this stuff. And what ended up, he said, okay, I could, I would like to participate in implementing it, but he ended up not joining Technion. And he said, I have this master's student who's also been working with me on PCDs and things like that, and by the name of Alessandro Chiesa. I said, okay, let's fly both of you guys over. I have a few students from a course I gave. Let's start this thing. So I had ample funding, took a bunch of students to implement these quasi-linear PCPs. And we wanted to start from C programs and compile them down to proofs. Now, why on earth did we want to do this? If I had to answer back in the day, I would say, well, I have 1.7 million euros. I don't know what to do with it. There's only so many pencils that I can buy as a mathematician. We'll publish a few papers. Students are going to get funded. No harm in that. Okay. Now, 5 years later, there was already a bunch of code being written. It moved very, 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 very slowly and was extremely inefficient back then. We were still working mostly on the PCP side of things. I was ending a visit at, a sabbatical in the Boston area, and I thought I might as well go around and give talks about this sort of implementation stuff, which I've been spending many hundreds of thousands of euros on and many years of work, and we even published a few things about it. So I was mostly going around universities, and I tried explaining, you want to give motivation to why this code is being written. And I had a number of motivating examples, and none of them quite made sense. But around that time, I heard of this thing called Bitcoin. I actually heard about it a few times before, but I always dismissed that thing as like impractical and non-interesting. But I needed, examples, like motivating examples for why am I doing this, and I stuck Bitcoin in the presentation, and I noticed that one of the talks that I was going to give, I think was at Stanford, was right near a Bitcoin conference in San Jose. So I reached out to the organizers and I said, why don't I come over and give this talk there? So, theoretical computer scientist walks into a blockchain conference. This was the most electrifying conference I ever attended, no offense to Eurocrypt, and it was the one point that changed my life. It was very electrifying because prior to that I was only at academic conferences that are very interesting and intellectual, but this was this conference was it had a kind of Woodstock feeling to it. People came from all over, drove all over the country because they felt that history is being made at that very place. I think the price of Bitcoin just went up a little bit. And it was just, I just loved this whole wild atmosphere. But also, the most amazing thing to me was that when I came off the podium, and remember, I was walking among academic institutions giving these talks. People were like, glazed eyes, yawning, saying, oh, very interesting, and like no follow-up. So I go down off the podium. Not many people attended the talk, but a lot of the Bitcoin core developers were there, and they asked a different set of questions. They asked, okay, where's the code? I said, why do you care about the code? And they say, what do you mean? We're going to do 1, 2, 3, 4, 5 things with it. And I argue with them, and I said, no, you're joking. Like, you don't really mean this. And they said, no, we really need this code tomorrow, and we're going to start using it in our systems. So I had this very deep feeling that there's something very, very different and interesting here. And it took me, I think, a very long time to process and realize what it was that I realized there. But I was lucky to be basically the first person to go and say, hey, these cryptographic proofs can help with scaling blockchain. There were already people mentioning the privacy aspects of zero knowledge, but no one noticed within the context of blockchain the applications to scaling. And I sort of really, I was about, my work was about scaling. It wasn't even about privacy at all, and I was just peddling it all around, and I ended up there. Again, I want to emphasize, this was not premeditated. I did not know that I'll be an entrepreneur. I did not know why I'm implementing this thing. If anything, if I reflect back, because I was thinking, like, why did this happen? I think it happened because I had this, two things maybe about my personality that maybe some of you can relate with. Like, one was like, whenever there's, I don't know, there's like, I want to go my own way. Like, I don't want to do what everyone else is doing. So if everyone else is doing this kind of thing, there's something about me that says, I want to do something different. I don't know why. And the second aspect was that I always felt, even during those years, that, just like, there are many researchers I work with that were very, very happy and in love with mathematics. And to them, this was all-consuming and all they ever wanted to do. For me, it was not the case. Like, I think that I was always curious and interested in more than just the theory. So even in those years, there were a number of different projects that I tried getting involved in, like, things related to biology and computation, things related to even, detection of autism. And so there was this thing about, I'm not content enough with whatever it is that I'm doing that somehow led to this exploration. But it was not premeditated, and this is how things will go. And then what happened was around 2013 were a number of beautiful breakthroughs, GGPR and Pinocchio and QSPs, quadratic span programs, that basically showed a path, I'll get to this later, that shows how you can implement things with what came to be known as mostly SNARKs. And we started also doing that direction. So remember, we started this thing in 2008 from the PCP kind of angle without any elliptic curve cryptography, but suddenly this new thing came around and we started doing it. And then what happened was, and I'm putting here the famous example of the, there's this famous historical thing in the history of art, right, where there was the established Salon de Paris, where all the most famous works of art were presented. But then there was this other line of works that was just, not so much part of that conventional thing, and which ultimately did lead to things like Impressionism and so on, and that's the Salon de Refuses. So if I think a little bit about what happened in those years and also a little bit later on, was the major trend was that, okay, the way to go forward is with these elliptic curve-based things with very short proofs, colloquially known mostly as SNARKs, even though I'm very happy to see that here the common word is NISICs. And we were going on this path that was like less believed in and less fewer people understood what we're doing. But nevertheless, I told you like something about, I don't know, my personality or something is that like, oh, if everyone's going there, let's try going somewhere else. I want to pause here and tell you a little bit about now, like many years after. So we're already 12 years after that moment that I felt in my heart that blockchains and cryptographic proofs have something to do together. So I think I can now articulate a little bit better why is it that today, zk is so much a part of blockchain and it is not yet a major part of the world of cryptography and security outside of blockchain. So I want to articulate what my current understanding is. Why is this the case? So we'll do a stop here and then go back to this story. So you have cryptographic proofs and you have blockchain. And these are two very different technologies, but they actually have the same goal. They deliver the same thing by different means and complementing means. That's what I realized. And this thing they deliver is really integrity. It is knowing that the right thing is done when you're not watching. And blockchain delivers it in one way, which I'll explain now, and then I'll say a little bit about how cryptographic proofs do this, even though I think most of you probably know this. So I prefer this term. I told you, everyone's going there, I want to go somewhere else. So I really, blockchain is very technical and talks about a chain of blocks. I prefer the term integrity web because it's actually like the World Wide Web. It builds on top of it and it delivers something unique and important, which is integrity. So let's put it in context. There have been many cases back in history where some new economic capability or technology arose, and then usually you have a few who are savvy or fast enough or lucky, and they exploit it, usually taking most of it to themselves. And then at some point, society, sometimes it could take centuries or decades, society sort of says, hey, wait a second, this isn't fair. Let's do things a little bit differently. And of course, this happened with agrarian societies, with the Industrial Revolution, and it may be taking, I hope it will take place in the digital space, which is the most important economic area of activity today, if you look at top valued companies. And certainly these integrity webs are part of the fight to make this thing a better world. So integrity webs are infrastructure for social constructs. I want to emphasize this. When people talk about blockchains, they usually talk about hashes and electricity and cryptography and maybe even zk. I think that's not the right way. It's not the way I think about it. It's a technology with a certain purpose, and the purpose is to build infrastructure for social constructs. So what are social constructs? Money is the most famous social construct. These are things, databases, registries, which carry immense value, and all of this value is based on their being both inherent integrity, that they operate as you expect them, but also perceived integrity, that there's broad social consensus and realization that they operate as intended. Okay, so those are social constructs, and money is the most famous social construct, but you have also governance processes, decision-making rules, you have registries of various forms, marriage registries, property registries, and so on and so forth. All of these are social functions. They carry immense value only as long as there's wide consensus about their integrity, and they operate with integrity. So this integrity web kind of way of doing things is a new way to get the same end result of implementing these infrastructures, which today, most of them are implemented by nation states. Previously, it may have been churches and religious institutions. Prior to that, it was probably the elders of the tribe who were the ones entrusted with running these infrastructures. Okay, and there are three novel aspects to the way these integrity webs operate, and you need all three of them. So the first one is broadness, often known as decentralization. Told you I like to give terms that to me make more sense. I also like positive sounding as opposed to double negation. So it means that the way you build this infrastructure is that it is based on there being a protocol that is open to everyone, and you actually want as many people to participate in operating it. So again, always think about, let's say, the banking system or payment networks today. This is not how they operate. You are not invited to be part of the network that operates your banking or payment system. Okay, but in blockchain you are. And actually, the more of us that will operate Bitcoin nodes or Ethereum nodes, or in our case, StarkNet nodes, the better off we'll all be. The second and most mysterious aspect, and of course this is, I think, the most beautiful and profound part of Satoshi's invention, is that of incentivized integrity, which says that the protocol defines a way to distribute value, usually in the token of that network. And the purpose of this distribution is for there to be perceived and inherent integrity, right? The reason the mining rewards and the fees go to miners in all of these blockchains is in order for there to be a realization of society that this actually makes sense, and my Bitcoin will not be confiscated because the miners are incentivized and they get paid, and if they actually go against the system, which they've paid so much in electricity and hardware, then they will be screwed more than I will be screwed, something like that. So, and the third, again, this is not how our conventional banking system works, right? Where everyone is invited to participate and you will be rewarded by the algorithm, by the protocol as you do so. And the last part is public verifiability, which is also extremely important. Everyone is invited to verify and check that everything about the system is operating with integrity, from the code, which should be open source, up to all of the transactions. Now, again, this is not how the banking system works. So we have this magnificent, marvelous innovation that I think resonates more with aspects of freedom, empowerment of individuals, free society than the current system, which is the underpinning of the integrity web. And it delivers integrity. Okay, but as you can see, if you want everyone to participate as operators, and if you want everyone to be able to publicly verify everything that is being done, then you're going to sacrifice something. And you actually sacrifice at least two things. One is scale, the other is privacy. But the focus of my, and actually, cryptographic proofs solve both. But the focus of my talk is about the scaling aspect of cryptographic proofs. So you have this system that operates marvelously, but it has very limited scale, and you cannot scale it up in the easy way of saying, okay, let's just 100x the number of transactions, because then people would drop off and you would lose, this would go away from its core principles. So that's why, the truly big and most important blockchains have very, very limited scale. And that's exactly where the second part comes in, right? And you can see that they complement and each other, right? It's a little bit like what Archimedes said, give me a place to stand and I will move the earth. So in the context of blockchain, right, we have, or in the context we're talking about, this integrity web, something very slow, but it has immense integrity. You can really, really trust it. And how do you use it? Well, there's this, I've quoted this sentence so many times. So this is from the beautiful paper from the 1992 BFLS, Checking Computation in Polylogarithmic Time. And here's a quote from them. A single, they invented, this is part of the early PCP results. They show that a single reliable PC, right, if you have this place to stand on, if you have this thing that you can really trust but is very weak, well, it can monitor the operations of a herd of supercomputers with powerful and unreliable software and untested hardware. So how does this work in the world of blockchain? Well, you have this integrity web. It's this PC. It's very slow, but you really trust it. And now you can use it to enforce integrity on vast amount of computation that you have no assumptions about, right? And that's the beauty of this. This is the love story between crypto and cryptographic proofs. And again, I was fortunate as I was walking around peddling mostly in academic institutions to be the first talking about scaling with no good use in mind to sort of stumble on this thing. And if anything, if I can take any credit for this, it's the only thing is that I listened and heeded the call, right? I didn't say, oh, it's a bunch of crazy, I don't know, anarchists, and let's go back to talking to the academics. I sort of, I heard the calling and I followed it, okay? So, and this is, I just want to, if we can, so this is just the first minute for my talk, if you can play it. And this is how it sounded back then, as I was realizing this. Can we play this, I wonder? Oops. Wait, how do we go back? Okay.
I'm going to tell you about a project that we're very enthusiastic about, and I think it can also help the Bitcoin community. It's an enabling technology based on a breakthrough in theoretical computer science that I want to describe to you, especially focusing on the applications to the Bitcoin community. So I'll start with some examples of the things we can do. And let's take some things the way they're done today with Bitcoin and the way we can change it and make it better. So today when a new Bitcoin node fires up, what it does, it downloads all of the blockchain from the Genesis block, and it needs to verify all of the transactions there. If our system is used, which implements succinct computational integrity and privacy, you could do it much more efficiently. The new node that fires up just downloads the last hash, and then it downloads a very short signature that some other node verified all of the blockchain.
Okay, so let's see if we can, here I can go back. Okay, so this is what it sounded back then. I didn't realize it then, but today as I'm telling this story, this is what I think I realized. And I meet a lot of people, both coming from academia and also from industry, that want to use, let's say, zk in many, many, many places. And unfortunately for, let's say, the zk researchers and entrepreneurs, in many of the conventional models outside of blockchain, you actually have repeated games, and you have reputation, and you can sue someone if they don't operate with integrity. And it's great for society, but it's really bad if you want to build a business on this, because in so many, I would love Google to prove to me that it's handling all of my traffic with integrity. But if Google said to me, we'll do that, but you'll have to wait, let's say, 100 milliseconds more every time you press send, I can tell you I'll say, no, don't give me this. Not to mention if I'm asked to pay for it. And I think it's this kind of realization that, even though zk someday will be used everywhere, today, once you have things like reputation and ability to sue someone, these proofs are just very, very cumbersome, sadly, okay? So there's also another consequence from this. As we look at, the blockchain industry today, we don't yet know whether true decentralization, this true vision of Satoshi, that it will be really based on this decentralized network, will be the end game, or whether the end game will be that it's just new financial rails that the banks are going to use. But I have very high conviction that if it's the latter case, then actually, company like zkSTARKs will either need to pivot to, I don't know what, like cybersecurity or something, or will cease to exist. Because if you have the conventional world using whatever they call blockchain, it means you don't need cryptography. Well, you don't need zk proofs. You can just have people signing on stuff and saying, trust us. So I have also very high motivation in terms of our business success for this not to be the case. I want to go back to this story. As I said, the Salon de Refuses, at least this was the feeling that I had, that and part of it was that, so right after this thing, and when SNARKs became a thing, the very short elliptic curve-based stuff became very popular, we of course also contributed to this. So Alessandro, Eran, Madar Zvirza, and myself from our sort of PCP researching stuff moved over also to doing that. We joined teams with the John Hopkins team of ZeroCoin, Ian Myers, Matt Green, and Christina Garman, and we wrote a paper called Zero Cash, and then this was picked up by a team, Zuko. His name Zuko, he wasn't born Zuko, but he changed it to Zuko many years before this thing happened, but this is all written in the stars somehow. So Zuko was the CEO of zkSTARKs, and zkSTARKs came around, and this was the first product used, in the world, in the wild, that uses general purpose zk for something. And this actually, zkSTARKs actually uses the zk kind of zk, not as blockchain uses, the other kind of zk, which isn't really zk. Anyway, so with this, like SNARKs and zk became a really big thing. But that's on the path that, this is the Salon de Paris. We continued working on this sort of more PCP-based stuff. And most of the papers were rejected multiple times. And, when they were accepted, this was like often to low-tier conferences. And no one really cared about this stuff. But, as I said, I just strongly believed in this thing, which is more like PCP-based, doesn't have number theoretic assumptions in it. And in 2018, we had all the missing links, and we founded Starkware, the first CEO and my major co-founder, Uri Kolodny. We got a prover out there, Stark prover, that was running in production a year later. Throughout this period, everyone is talking about and implementing SNARKs. Everyone is saying, all of this stuff has proofs that are too long, it's inefficient, it's never going to work. We built more and more systems with it, mostly alone. We improved the soundness through a lot of mathematics, like the proximity gaps paper that now is often used. We built dedicated special purpose virtual machines for getting something that would be both safe in the context of blockchain and also have very efficient Stark proofs, that's Cairo. And we expanded the set of, fields, finite fields over which you can implement these things very, very efficiently to essentially include all fields you can hope for through things like using elliptic curve groups and most recently the circle curve over Mersenne fields. And now we have the next generation prover, which is the very best in the world, but I'm not going to share with you details about that. Today we're in a situation where pretty much all of the blockchain zk, so again, it's not real zk, it's like most of these are scaling using cryptographic proofs. Scaling teams are using Stark technology, and more are joining. And so sort of now this sort of line of work that was a little bit started off as Salon de Refuses is embraced as the way to solve blockchain technology, the blockchain scaling issue. And I want to give a little bit of, historical perspective as how I see from these different branches and the connection between them. So it all starts with interactive proofs in zk. And then there are, again, there's just so many, there are dozens of important works, so, I'm omitting a lot. But there's the sumcheck protocol, and IP equals P space. There's polylog verification that goes all the way up to NEXP. And there's the PCP theorem that is catered at NP, but has a bunch of, so both the polylog verification and the PCP stuff is very much based on, all three of these are based on a lot of algebra of polynomials or finite fields. And then there's this very important additional thing that comes from left field, which is pairing-based cryptography. And in 2008, 2005, 2008, a bunch of things just miraculously happen and coincide. There's the Proofs for Muggles paper that basically says, you can take the sumcheck protocol that was for IP and inefficient, but you can actually make it work for practical proofs. There's the quasi-linear PCPs, which, as I just explained, was not about trying to implement anything, but happened to have a lot of the ingredients that were then used in Starks. And you have this very influential linear PCP paper, Ishai, Kushelovitz-Ostrovsky, that says, well, out of this, most of the PCP machinery is very, very complicated, but maybe we can circumvent it if we just work with additive homomorphic encryption. And then these led to things like inner product arguments and quadratic span programs and what the world of blockchain calls SNARKs. And then you have the stuff that is more based on less number theory, less elliptic curves, more polynomials and algebra, which has led to things like Fry and Stark and GKR-based systems. And if I summarize what I did in my research over those years, so I took something that was impractical, but it's this line of works that is based on PCPs and low-degree polynomials, and removed 2 letters from it in a variety of ways that were all of them motivated by just making the damn thing work. Because initially when we started, it was very hard to imagine that this could be implemented in practice. Now, what is the definition of a Stark? The letter S stands for scalable, which means 2 things. You want to have quasi-linear proving time, and you want to have polylogarithmic verification time. And T stands for transparent, which means that there is no trusted setup, everything is random public coins. A few reflections. I'm often asked about, Stark versus Snark, and my first answer is, well, those are not the only 2 terms out there. As I just said, everyone here I heard talks about NISICs and SNISICs, and there's SNARGs and CS proofs. So really, I think everyone should use whatever they like and they feel best with. All of these, different definitions, they capture different aspects. I will say that, some call Starks hash-based Snarks, some call them transparent Snarks, that's fine. I'll point out that the N in NISIC, SNISIC, SNARK stands for non-interactive. And I hereby do declare that we're going to deploy Starks on Bitcoin, and when we do so, they will use interactivity. Why? Because it gives you shorter arguments, because basically Bitcoin already does this sort of proof of work grinding that gives you 80 bits of security for free. So we're going to use it. And in that case, you can look, we're in a world that people call systems that are non-zk, zk, so you can talk about these things as snarks or nisics, but you'll be going a little bit further from the definition. Within the world of blockchain, usually when people talk about Snark, they mean elliptic curve-based stuff, and when people talk about Stark, they either mean stuff that Starkware uses or stuff that is using Fry and usually small fields. And as I said, when people talk about zk within blockchain, please be aware that they mean not zk. By the way, it's one of these windmills I'm trying to fight always. There's this thing called zk rollup. I say, no, let's call them validity rollup because most of them don't have zk in it, but it's a lost battle. But I hear you. Anyways, so now the rise of Starks as blockchain technology. The latest news, everyone today in blockchain world agrees that zk is the end game. And when they say it, they mean mostly for scaling, even though privacy as well. It's just that privacy is, I don't need to tell you cryptographers, right? Privacy is something everyone wants, but no one really cares about when they, so it is what it is. Scaling means money, you can save dollars. Now we're talking about something that people want. Okay, and as I said, zk, when they say zk is the end game, they mean the non-zk, zk is the end game. And Starks are rising in favor, like almost all of the major teams that are interested in scaling blockchain, they all of them use Starks, Fry, small fields, stuff like that, no elliptic curve. Many of them, there's a specific subsidy over Ethereum that allows you, if you use a very specific snark, you get a subsidy. So some of them wrap at the very end with a snark just to get this subsidy. And now why? So I think the shortest answer, why is it that people are using these Starks over the elliptic curve stuff? The simple answer, I think, is that 32-bit arithmetic, which is what most of these teams are moving to, is just practically on x86 and ARM systems. It's something like 100 to 120x faster when it comes to multiplication. Now, if you do the numbers, it should only be like 16x faster. It's not, because you have vectorization, and you can't use vectorization for these very large integers. Practically speaking, when you measure it on standard hardware, it is 100x faster, and that really, really dominates. It's also post-quantum secure, and these days people are worried a little bit more about that. And also the fact that there's no setup needed. It's not just about the security, it's about the ability to upgrade the system in a very simple way. So I think these are the reasons that STARKs are dominating. Another reason, and this is to the credit of Starkware, is that we just showed them to be very, very practical. So we settled on our systems over $1 trillion of trading. We minted over 200 million NFTs, did over 1 billion transactions, and saved over $1 billion to the users of these systems. So this has convinced the world that it's not just theoretical, but extremely practical and useful. Our system today has the highest TPS, the lowest cost per transaction, and a whole bunch of other things that I'm not going to go into right now. So the last part is I would like to tell you a little bit about some Stark research nuggets. I want to tell you a little bit about FRI, Deep FRI, Correlated Agreement, and STIR. And in doing so, I would like to... This is the most theoretical part, but I'm just going to skim over things, and maybe my hope here is to maybe interest you in some research questions, to read a little bit more. Okay, so we first of all need to recall what is a polynomial commitment scheme, and here's the ideal functionality for a polynomial commitment scheme. It has 3 players. So Alice specifies a field and a degree that she's interested in, and then Bob sends to this trusted party, Tom. Tom is like a god or an apostle. You can really trust him. So Bob will send some polynomial of degree D over that field. Okay, a univariate polynomial, but you can make this also multivariate. And the point is that then Alice will query Tom for a value of the polynomial in the field, and Tom will answer honestly. Now, if you have this ideal functionality, then you can get amazing proof systems with very optimal proof systems. So really, everything about within the world of SNARKs and STARKs and GKR and everything is about how do you implement this functionality when there is no Tom, there is no trusted party. So you only have Bob and then Alice. Okay. So we'll get there, but we need one more thing, which is an IOP. So the original definition of IOP actually appears in the paper of BFS from '90, but it had a revival in 2016. Reingold, Rothblum, and also myself with Alessandro and Nick Spooner. So what it is some combination of IP and the PCP model. Bob sends an oracle. Alice sends randomness, Bob sends another oracle, they repeat this a few times, and then at the end Alice queries all of these different oracles and decides whether to accept or reject. So within IP you send messages but not oracles, and within PCP you do this, let's say, only once. So this is some combination of both. Here's a reflection. So I have all of these reflections. Like, why did we start caring about IOP back then and sort of reinvent it or rediscover it? It was because we wanted concrete efficiency for these PCP systems. It turns out that when you look at PCP systems as they were originally, you have a bunch of constraints. Each one of them would require its own proof. If you have an IOP, you can somehow merge together using randomness many constraints, and this led us to sort of rediscover, reuse this IOP protocol. So looking at concrete efficiency, because we really wanted to implement something in practice, led us to sort of revive this model, which these days is very popular. So now we have an IOP, and I want to tell you about an IOP of proximity for solving the problem of, you have this oracle access to a function, and you want to know whether it is a degree D polynomial. Think of the degree D as being much smaller than the encoding of the function, but also something too large for you to just query in full. And you want to distinguish between that case and the case that the function that you're given oracle access to is very far from that. So this is the fast Reed-Solomon IOP of proximity, which underlies pretty much all of the efficient STARKs that are in use today. So I want to explain how it works. Consider a case where your field F has a multiplicative group that is FFT friendly. So the size of this multiplicative group is 2 to the k. And suppose you have a function going from this group to the field. Now, if you do, so think of this as, let's say, the roots of unity of order 2 to the k. I mean, that is that group. Okay. So if you remember how the FFT works, the FFT takes a function evaluated on the roots of unity of order 2 to the k, and it does the first step, it sort of separates it into two arrays or two subfunctions. And each one of these subfunctions is also a function on the roots of unity, but fewer roots of unity. Okay, so the first step of the FFT splits your function into two functions. And they are functions from a subgroup. And then you continue with this, right? That's how the FFT works. Well, there's also this deterministic connection between every pair of entries in the big function f corresponds to one entry each from the two subfunctions, right? If you take the values at x and minus x, it will give you the value in the two functions of x squared. And you can deterministically go from one way to the other. Good. So here's a claim that is easy to verify, but I'm not going to prove it here. If it happened to be the case that the function f that you started with happened to be of degree d, small degree d, then if you look at the two subfunctions that the FFT gives you, they will be of degree d over 2. So happens. And this gives rise to what Frey does. So Frey says, well, if you want to prove to me, I have this big problem. I want to know whether this function is of degree d. Let me convert it to a problem of half the size and half the degree. And how will I do it? So the prover Bob has sent over Oracle access to f, which gives immediately these f0 and f1. What Alice sends is a random z and asks to repeat the same process for the random linear combination, for the z linear combination of f0 and f1, right? And if f was low degree d, then the new function g will be half the degree, and we can repeat this. Moreover, there's a very immediate test that comes to mind. We can look at f at the entries x and minus x for a random x, and we can now check whether the relevant entry in the function g is what it should be. So this also begs for a test. And notice we reduce something of size d to d over 2, and there's a protocol that makes pretty much two queries. And if you sum everything up, what you get is an IOP of proximity for low-degree polynomials that has linear proving. It was the first proximity test for Reed-Solomon codes or for any codes with linear time proving. Logarithmic verification, very, very good constants, very efficient practically to get the proofs and to verify them, post-quantum secure. The three questions that I want to talk about soon are soundness, how do you get a polynomial commitment scheme? I mean, how do you know the value of the function outside where it's committed to? And how do you move to generic field? But I want to tell you a little bit about reflections. So how did Frey come about? It came about because we were implementing these PCPs, the quasi-linear PCPs of Ben Sasson Sudan, and was extremely inefficient. And they were inefficient because there was some problem with the soundness that by now has been removed. But when you the concrete soundness just happened to deteriorate very, very fast in the context of Ben Sasson Sudan. So it was very fine asymptotically, but practically there was a big problem with it. So it was about trying to get better concrete soundness and better concrete efficiency that led to this thing. And this also fed into the IOP model that became very, very useful here. Because basically, if you think about a PCP, there's a lot of information being produced by the prover, but very little of it is consumed. So there's something more economical here. Another thing I want to say, I was extremely excited by it. I thought this is a spectacular result, but the academic world did not think so back then, And this is just an example. This happened with all these other things. Okay, so what about soundness? And so if two functions are low degree, if you take any linear combination of them, that thing will still be low degree. That's the completeness side. Soundness should be the other way around. If it happens to be the case that a random linear combination is often enough close to low degree, you would like to go backwards and say that the two functions that generated this thing are also low degree. And this turns out to be, well, A, correct, but also extremely challenging to prove, which is what the correlated agreement, the proximity gaps paper does. And here's an informal version of that theorem. If for random z, the function gz, which is the linear combination of f0 and f1, has epsilon agreement, some very small agreement with a function of degree d, and this happens just for a few z's, doesn't need to happen a lot, then there is actually an epsilon fraction of the domain on which the two functions, f0 and f1, are exactly degree d. And this is extremely important for knowledge extraction. So epsilon is today the list decoding radius. It's roughly square root of the degree divided by the size of the domain. And a few z is very small. It's like roughly polynomial in the degree over the big field from which you're sampling f. And reflection. So why correlated agreement? Again, we needed concrete soundness, shorter arguments. Curious stuff is that the proof of this is the first real-world use case of the Goswami-Sudan list decoding algorithm. So the place where Goswami-Sudan list decoding algorithm is in this result and in the knowledge extraction of STARKs based on it. And here's a very cool conjecture that I would love people to work on. Is the square root bound needed? Can you get the similar result with not square root of d over n, but rather d over n? If you get that, you can make Frey arguments 2x shorter, or at least prove that they're sound when we do it. So it's a very interesting result. It's deeply related to questions about the list decoding of Reed-Solomon code, the Johnson bound, and there's a lot of literature on that. So how do you get a polynomial commitment scheme from this? So how do you answer, how do you know what the value of a polynomial is outside the domain it's been defined on? So the answer is you ask Bob plainly and take the answer, but then you change the whole function to which you apply your Frey protocol by the answer given by Bob. And you do this quotienting. You subtract the value that Bob has given to you, and you divide. Now you're supposed to have a 0 at that point, right? Because at point... And then you can divide by and lower the degree of the function. So basically you have this transformation that changes the function locally and gives you what you want. This is also known as quotienting or out-of-domain sampling. And why did we do it? Again, we needed concrete efficiency over binary field. So this concrete efficiency just gives pops up time and again. A lot of deep theoretical results came from needing to do things that are very concrete when we were building systems. And this goes on all the time. And why is it called deep? Well, obviously because we wanted deep Frey. But there's also, I can open up the acronym. It's less interesting. Practically, it's very much used, but actually not in the context of Frey, but in another context. I'll just mention one last result. And that is, why deep Frey if you can stir? This is a beautiful result from last year, Alessandro and co-authors. So with Frey, you can also do a Frey reduction where you sort of do a 4-to-1 reduction in the domain instead of 2-to-1 reduction. And in this case, you will reduce the size, the domain of the function by a factor of 4, and then you reduce the degree by a factor of 4. So Stir says, let's do something a little bit smarter. Let's reduce the size by a factor of 4, but actually ask for an evaluation of a function that is only twice smaller in degree. And this leads to you making fewer queries down the line because you have better rate in your code. But the problem is that now there's no immediate connection. There's this sort of 2-to-1 or 4-to-1 connection between the function f and the next function g disappears. Thankfully, you could use out-of-domain sampling and quotienting to actually solve that problem. So I want to recap everything that we said. Cryptographic proofs love crypto because they are two technologies that complement each other. There are two means to the same end, and that end is integrity. I hope I impressed you with some Stark research nuggets, at least enough to be curious and read a bit more and learn and hopefully make progress on these very interesting questions. these very interesting questions. And for those of you contemplating ever going into entrepreneurship or blockchain or so on and have problems, well, please reach out. Happy to share more insights, stories, but at least my own story was that this was a very winding path, and it certainly was not how I thought things would play out. Thank you very much.
We have time for some questions.
Hello, thank you for insightful talk. I wonder, from the perspective of social area, should the transactions be private or public in public blockchains? What's your opinion on this?
Sorry, so should the transactions
be private or public in public blockchains?
Okay. I definitely would love privacy to be a feature, let's say, I think it's very important that we have privacy on blockchains. I'm just saying, now as a business person, if we want to be sustainable and succeed, it is much more reasonable to first solve scalability. But I can tell you that my company were very much interested in working on privacy. The problem is that it's not the technology that's hard, it's actually the decrease in UX and also the regulatory friction. It just means you need a whole new set of wallets, and a lot of exchanges are not going to accept stuff, and it becomes very cumbersome. The making things zk, like adding zk to these zk systems, is very easy. It's all the other stuff that is related to UX and usability that's hard, and people, frankly, don't care enough about it.
Any other questions? Yep.
Thank you so much for the great presentation. So recently Vitalik posted about replacing EVM with RISC-V. So what would be the cons and pros if EVM be replaced with Cairo and not RISC-V?
It's a terrific question. My team is working a lot on publishing something on that. So, okay. Ethereum right now has this virtual machine called the EVM, the Ethereum Virtual Machine, and indeed Vitalik has very recently said, let us maybe accept as a next generation virtual machine for Ethereum something that is RISC-V based, where the reasoning is that RISC-V is recently pretty popular among zk proving systems. Okay, and we have a different virtual model. So I'll tell you what we're currently writing. We're saying, here's how we think about it. A blockchain virtual machine, you need it to be both sanitized in terms of not reaching out to the file system, not having non-deterministic behavior, not having all kinds of exceptions and stuff, and you need it to be sandboxed when it's running. Now, we suspect that if you the pros of declaring, let's say, RISC-V or any other standard instruction set as the next generation VM is that you have all of this tooling and you have compilers and so on. However, once you add this sandboxing and sanitization, you're already going to diverge very significantly from it. When you add things like gas metering, the fast execution suddenly becomes a real issue. So it's not clear you'll get that. The other reason is to say we also want a provability of these things. There, it's pretty clear that they won't be extremely provable because they don't have proving in mind. Okay, so what is the approach that we took, and we actually advise Ethereum to consider something like it. Cairo as a VM, for instance, has no registers. Why? Because when you construct arithmetization for a proof system, registers are something that are going to be needed. Basically you have to commit and sort of put them everywhere. It makes a lot of sense in the context of silica where you want stuff to be on hand, but in proving you don't have. So Cairo has no registers. There's like literally 3, but there are no registers. The program counter, an allocation pointer, and a frame pointer. But so you want something that is zk friendly. There's also continuous memory and all kinds of things. Okay, so what did we do? We have an intermediate language that's called Sierra that does the sanitization and sandboxing, and you can compile into it, and that sort of takes care of the blockchain stuff. And this thing is then compiled, oh, and it has also gas metering at compilation time. And then you have that compiled into a ZK-friendly language. So we think that is the best of approaches. The big downside of it is that you will get something that is non-standard today. So you're going to need tooling for it. But my claim to Ethereum is you are uniquely positioned to set the standard. And if you say, here's a new VM, be it Cairo, let's say a next version of something like it, so okay, it won't be RISC-V tomorrow, but you will have extremely, extremely good tooling for it within 3 to 5 years.
That makes sense. Thank you.
Okay, maybe the last question from Nicola.
So the question is your technology permission-free? So for example, can you implement it without the permission of Ethereum or the permission of Bitcoin core developers? And also, is it possible that you will actually fail to scale Bitcoin because it's easier to scale Ethereum?
Well, okay, today we're scaling only Ethereum and not yet Bitcoin. Okay, but we have announced that we are moving forward also to scale Bitcoin. With Ethereum, indeed, we did not need the permission of anyone. That's really what's great about a system that is Turing complete. We wrote our smart contracts and we were done with it. With Bitcoin, I would say, okay, the best hope, and we're trying to advocate for it, is that there's this soft fork that is called opcat. They add an operand called concatenation, and now you can just barely fit in a Stark verification. So we're trying to advocate for that. There's actually a very ingenious line of work that spearheaded by some folks from my team, Avihu Levi and Victor Kolobov, about how even without opcat, using collisions, also Moni Naor is involved in this, how you can, within the existing Bitcoin world, basically using the fact that it's easier to get a two collision rather than a 3 collision. So capitalizing on that to actually put Stark proofs and covenants today on Bitcoin. And I think they're making very, very nice progress. So I think we may even be in a situation where we don't need permission and we don't need opcat in order to settle Starks onto Bitcoin very soon.
Okay, then I would like to thank Eli for this awesome presentation with a small token of appreciation, also in the name of the General Chairs, and another round of applause, please.
Thank you. Thank you, Serge. Thank you. Thank you. Thank you so much. Thank you.